So the first speaker is Emil. I wanted to put Emil to do the opening act because so I just some biographical things that I think. So Emil is from Romania.
Yeah.
So he got his Bachelor of Science and Master of Science from the University of Bucharest. He went to Houston. He did another Master's of Physics, if I'm not mistaken. I'm taking it from the webpage, but
good.
He did his PhD in Rice University here in the US, and his first, I suppose, postdoc was in UC Santa Barbara under Walter Kohn. He's now deceased, so Rafael got the Walter Kohn Prize for my CV. So what, 2 years ago?
2 years ago.
2 years ago. So, and now he's in Yeshiva University. Emil, thank you very much for your help and support this conference. Owes you a lot.
Thank you.
So please, you have to announce. So I'll share.
Thank you very much, and thank everybody for coming. And I think the topics are very interesting for this conference. And I for sure, looking at the titles, I can learn from each of the talks that we will have, and I hope it will be the same for everybody. So it's not, like we said, it's not a large meeting, but it's our meeting, so let's make the most out of it. So I'll talk about an interesting development, Chern insulator and Chern models, and I was talking, just having a discussion before. Can there be anything new about these Chern insulators? I mean, we were talking about that since 1980. And Nigel, I will assume you know Nigel Gibson. He can be as abstract as you want. In fact, that's his style. He goes into abstract to a point where everything becomes trivial. So he was explaining me, or at least that's what he was telling me, that he explained to me this thing that I will present today several times, but I didn't react it, or I didn't, because I didn't have the background to understand what he was talking about. So he visited me last October, and among other things, he said, "Let me tell you again about the corner of the blackboard," and then it clicked right away. So we wrote a paper, and it's in a physics journal, so it's his first and only paper in a physics journal, and he's really proud. He told me that he printed it. So I have something to say about the Haldane model. So 1988 was a Hall effect without magnetic field, so it's sort of an intrinsic Hall effect, and it came like magic. So you would say it was a stroke of genius, and one uses the honeycomb lattice and second nearest neighbor couplings. But these days we know that the models belong to you don't have to use the honeycomb lattice, you can use square lattice, and you just have to use two sides per the two orbitals per side, and you can write again this model. So I say not coincidentally, because the model represents the non-trivial K-naught theory class of C star Z. So we take this one for granted these days, but when writing this, I was thinking that Herman is in the audience, and Jean and Hermann and Johannes, they were doing heat theory in the 90s. If they made this connection back then, they could have started the topological insulator revolution back then. So it's not a trivial thing. So it's actually, now we take it for granted, but will you agree, Herman?
Yeah.
So if something clicked and you say that this Haldane stumbled on the generator of the K-naught theoretic class, you immediately will say, oh, there are so many more models over there. You could have discovered the A3 class and maybe not time reversal, but you could set the wheels.
Your background.
No. Yeah, you could set the wheel in motion, but so it was the physicists who pushed the whole development, and Jean's approach and the C-star theoretic framework, they give me a job and to enjoy all this, because otherwise I would probably do just numerical modeling. In fact, I will show you some of my earlier works where I did a lot of modeling, and so I had a workstation, they were piled on the wall in my office. I didn't want anybody to touch them. I didn't want them to go to a center. And they were running day and night, calculating phase diagrams of these systems. Good. So, in fact, this is one of them from 2013. And I chose to introduce these new things about Chern insulator by taking a little bit over the history of how I see the thing. So here we are on a pristine lattice, but we would like to go to disorder samples because here is where the magic of these topological insulators is, and in the C-star algebraic framework, we are just making the jump from the C-star algebra of this abelian group to a cross product. So what happens? So in these simulations, we have Haldane model with the disorder. It's large enough so that the spectral gap is gone, so there is no gap in the spectrum. There is temperature, so you see here temperature, and I am using here the Kubo formula with dissipation, which was developed by Jean and Hermann, and I was very happy that I learned how to implement it on a computer in a fashion that gives me exponential convergence with respect to the lattice size. And if you have exponential convergence to the lattice size, then you can, then and only then you can approach the critical, compute critical exponents and so on and so on. So if you have only polynomial convergence, that's not good enough because that will influence the value of the critical exponents and so on. So
which model did you have here?
Yeah?
Which model did you compute this for?
So it's Haldane model with the on-site, random on-site potential. And then, so disorder is already disorder, and now I'm taking the temperature down. Okay, temperature goes up here, but we are interested in lower and lower temperatures. And if we look at the whole conductance, which is here, we will see quantized values. So it goes from -1, and then so I am varying here Fermi energy, but in an experiment you will vary electron density. And then there is one point where on one side it seems that whole conductance is 1 × 1 and the other one to 0, and we see the direct conductivity going to 0 on both sides. And if we look at the resistivity tensor, which is just the inverse of this sigma matrix, you get a picture like this, and you calculate this for many temperatures, and you discover that there is this one single point. So this is the type of calculation you need to do to convince people that there is a critical point, which then is a thermodynamic sort of phase transition, which separates the topological phase, the Chern insulator phase, from the trivial phase. Now,
just a question: did you push it all the way to compute the exponents there?
yes. So the exponents, it's 2.68. So it's
I mean, there's still people computing that.
still computing because they are still drifting. So the value is not set. So my value was consistent with the newer. That's right. So and then I tried for chiral symmetry, and that didn't work from just the invariant. So the scaling of the invariant is not the right quantity to look at to calculate the critical exponent. So I learned that from Outland. They have a nice paper saying
in dimension 1, no? This is 1D paper.
1D, yeah. So so let's see what is special, because we forget what how the periodic table or the classification table of proportional insulators came up. Yeah, they are edge modes or surface modes, but they refuse to undergo Anderson localization. So they not only exist, but they refuse to undergo Anderson localization, and therefore they can conduct charge current. And yes.
Question: what happens if you have periodic boundary conditions?
Yes.
You don't have the edge states. Is this how you calculate this under?
So, yeah, this one is with periodic boundary conditions, and so it's Kubo formula, no boundary. So it's not the transmission to a ribbon or things like that.
But I think we could. I don't think you need periodic boundary conditions. Maybe it converges faster, but we know it's self-evident. So even if you take large volumes, it should be okay.
I guess my question is because the last statement there, edge modes do not refuse to go Anderson localization. If you don't have the edge modes, then presumably all you can have Anderson localization and under disorder, and then I guess that's how you go from. I mean, how do I understand that under periodic boundary conditions?
No, so clearly this one is outside the context that's shown up here. So you will, for the last statement, you do need to put a physical edge.
Yeah, but I guess my question is, if you can Anderson localize all the states of the system under periodic boundary conditions, then
no, why do you say? Yeah. So here we have these are Anderson localized on this side, Anderson localized this one, and there is the exactly here there is the Anderson localization, delocalization, and then you are asking how can the edge modes stay delocalized while in the bulk you have you have an insulator. So you know the answer, or because that's what's happening here.
Yeah, I could make a comment, but it's a bit speculative. That perhaps what happens is you can localize n-1 state, and one remains fully delocalized. So it carries the Chern number.
Also, okay, so what is said here is that if you try to calculate linear functions, on this side, you cannot calculate exponentially localized linear functions. But when you talk about an insulator in the presence of disorder, an insulator is defined by transport coefficients. So an insulator is an insulator if the direct conductivity goes to zero as the temperature goes to zero. So that's what an insulator is. You don't need spectral or anything else. And it's a metal if the conductivity, direct conductivity, so this sigma xx diverges. And what we see here is that although we have a localization, the localization it stays here. So this is dirty metal, and here it will be. So this is a dirty metal where the sigma xx is finite, but it's still it's not zero, but it doesn't shoot up. And you are right if you are trying to see what they are different explanation for this phenomenon, depending where you come from. We have our. That's why we are working with this one, because we have a line by line proof that these surface states, H modes, do not undergo Anderson localization. Good. So we made the jump, and I was extremely happy. Cross product algebra, this omega encapsulated state disorder states, and there was a lot of things to be done. And from time to time we will hear talks from Chern and Johannes, which we will always start talking about groupoids. And back then, we said, why groupoids? Because anyway, it's all we can do everything in this context. So here it's the one of the resolutions. For example, there is index theorem which to hold. So we have an analytic index, sort of a geometric index, and for it to hold, we need this quantity to be less than infinity, and that quantity really tells us the spread of the occupied states, especially at the Fermi energy, and then you look at the right hand side and you see that it's related to a nonlinear transport coefficient in dimension 2. This is just the whole conductance. If you go to higher dimension, then it is derivation with the respect to the flux in different directions. And this index theorem says that if you want to change the value of this invariant, then this quantity needs to diverge, and that's exactly Anderson localization, delocalization conditions. So it shows that indeed on one, these are two thermodynamically different phases, because there is a quantity which is observable in the lab, which diverges as you cross from one value of the whole conductance to the other. And I want to mention this new work by Tom, because I think it settled this whole conjecture for the entire periodic table of classification table of topological insulator. I try to convince Tom to change the title from these technically looking things to proof of the entire conjecture. So that's why the Kitaev model doesn't have K groups. It's very simple. It only has Z or Z2 inside. Why? Because the classification is by physical means. The original thing was, okay, what are the crystals which do have edge states, but that's not enough. They do not undergo Anderson localization. That's what we call the strong full boundary correspondence principle. While the other one will be called the weak one, where you just observe their edge modes, but you don't know what's the fate of those modes when the surface is rugged or even the whole is rugged. Okay, so I was telling you that we were happy at this level. Things from Chicago, a group from Chicago surprised us, Irvine, and they were in fact the first people to demonstrate a topological mechanical insulator from Chern class. So what we are looking here are, in fact, these white things are plastic tubes, but inside those tubes they are spinning tops. And you don't see here, but they are connected to springs. And this whole thing was sitting on the ceiling. And I guess one day they were drinking their coffee, looking up, and they said, "How if we try an amorphous, amorphous thing, all we need to do is shuffle these things around." And they proved that amorphous system. So what happens? The spinning tops put a synthetic magnetic field on the system. So in fact, this is the simple mechanism to open topological gaps. You just twist an ordinary model by the area co-cycle of the surface hosting the point pattern, and that's condensed matter. We call it the pile inserting pile phase factor, and by spinning these tops in the background really enforces that mechanism. So they found the same again, topological edge modes, and Irvine flew to New York because I knew how to calculate Chern numbers in the presence of this author, and he asked me how you compute the Chern number for a completely amorphous, and was very funny realization. I didn't know how to calculate it, just didn't work. So my first approach was, okay, let's try and take like an imaginary square and try to bring it back to a lattice with some disorder. And you always see that no matter what you do, the number of points inside these boxes that you take fluctuates, and there is no clean way to do it. And in the same time, I was also working on twisted bilayer. And what happens if to succeed like this, you have to sort of find a way to label these points by elements from Z. So we'll try to start enumerating this using ZD. And I was trying the same for twisted bilayers, thinking, convincing, I was convinced that if I am clever, I will be able to label the points of a twisted bilayer by points of ZD, and of course, at the end, you cannot do it. So that's where I made the jump to this groupoid. Let's say we have this under our belt. We understand it. Could this be the key to deploying quantum Hall effect on arbitrary surfaces? Because after all, what else can you do out of more than random points? So before I will tell you that it's not the key. Actually, yeah, this page says it all. So here is such a randomly generated sample. So the way I generated this sample, I ask the computer to give me a random number between 0 and 60, and I was putting points, and if the points came closer to a certain radius r, which was fixed, I will reject that point, and I will ask for another point. And after a while, there was no more space to generate points, so the algorithm will stop, and it will produce something like this. So now, as I said, if you put a magnetic field perpendicular, then you see this kind of graph, and here is the let's say flux of the magnetic field through an area. So it's we could say it's the strength of the magnetic field, and we do start to see gaps appearing in the spectrum. If you look closer, those gaps are not clean gaps, so they are with the impurity states. So there is a finite density of states inside these gaps, and these are calculations by the methods I was telling you, and we can, in fact, see here Chern numbers being calculated and taking very nice quantized values. So, talk to mathematicians to convince them. You need to go quite far with these digits. Yes.
Is this on a finite system, or have you wrapped it periodic?
Yeah, wrap it in periodic. That's the weakness of this method. You have to wrap it in periodic boundary condition.
And you just get shown up for 0 and 1, or can you get higher ones?
Yeah. So here, this one should to 2. So this is this branch.
Oh, okay.
And there was another one here was supposed to develop here, but there was not the. I needed to go to much larger systems.
Sorry, Emil, what's your y? I cannot read it. What's your y-axis on the colorful flux?
Here?
Yeah.
So this is energy, this is magnetic field, and color is the value of the Chern number. And here is a section which was taken over here, is shown by this graph.
And by energy, this is the sort of like a Fermi energy that you're feeling, or
that's right.
so
Fermi
you're
energy.
blowing up.
So that's the Fermi energy. Fermi energy. If I put it here, then and for a given theta, I calculate the projection into the occupied states, and out of that projection, I calculate the Chern number using this formula. And what's the point here is that when you have periodic boundary condition, then position is doesn't like periodic boundary condition, so it's you have to replace this commutator with something else, and there is an optimal way to do it so that this whole thing converges exponentially fast with the size of the system. So there is an explicit thing what you need to replace that commutator with, and those kind of that simple replacement gives you this kind of results. In the book, I have calculations which actually go all the way to 12 digits of precision when there is no gap. Okay, so I'm saying not really. So there is still strong index theorems, and we know for sure that these edge nodes do not localize, but it's more complicated story. But what's the point here? So the gaps open here are very small. So when you put this magnetic field, gaps are very, very small. And the implementation of area cocycle twisting is a nightmare for triangulation of arbitrary surfaces. When we write grants, this is what the promise of topological architectic material. We imagine that you have a spacecraft being a space station, and you want to send a signal from some sort of a base to any point on the surface. So you need to create topological edge channels so that you can transmit this information. So then what you do, you should coat this surface with a topological material, and you would like to jam the resonators of the material on one side or on a strip, and the edge modes should, like we know they do, they should appear, and presumably you can do all of this from the inside of the graph. You just this material has a substrate of DS, which you can program from the inside, and you can jam the metamaterial on any domain you want. So now, if I want to generate to code this material with a tie-binding model, then, for example, this is the triangulation of this surface, and you see it's so complicated. So how will you put a topological model here? So if you try to, let's say, so this is a genus zero surface. I put a magnetic monopole inside. We are back to here. We are creating a magnetic field, but it will be just a nightmare to, like I said here, to implement this area co-cycle twisting. And at the end of the day, what you will find is these tiny gaps which will not do in applications. So what you want is like to put a model on a surface like this, and you'd like a good gap to open. The gap should be clean, and if I jam, so I imagine here there are, for example, acoustic cavities which are connected with channels. If I, for example, take this object and I dip it in water up to here, I should see edge modes going around here. If I dip it in water up to here, I tilt it and dip it, I should see edge modes. And you will see that if you take, so first I argue that random points, I mean, these are very irregular points, going by putting a synthetic magnetic field on this surface will not work. And then if you try any other model, you will see that they are all living in a plane. So they are living in flat land. So that is when Nigel explained me in this little corner, I immediately see that it's a solution to a problem which existed for a long time in topological architecture material. How you put a Chern insulator on a lattice like this. It's very interesting because whenever you 3D scan a picture, you get a triangulation, and in fact, there are libraries, standard libraries for just for testing, and this one is called Stanford Bunny. If you try to do finite element, finite distance, finite differences, any other things that involve triangulation, there is a standard library from where you can pull out models and work with. So this was one of them. Luckily, Mathematica has it, and when you access it, Mathematica generates a triangulation, and the triangulation, all the data for the triangulation is readily available. And in fact, now these days, I'm planning to take the 3D scanner and generate these triangulations out of 3D scanning with my students, just to hook them to mathematics. So you have to start with things that they can do, and then slowly ask tough questions. So it's interesting because as we were having lunch with Nigel, I said we saw a bunny, and it was in a botanical garden, but it's next to Prodan where Camellia is. We saw a bunny, and I said, oh, we can put it on a bunny. And we just found the bunny in the library, and we said, okay, let's go with the bunny. So I have I just showed you. We do have the movies where I will have an edge node going around this bunny. So you will ask me then, so I will show you a geometric calculation that gets us to the universal Chern model, and then you will ask me if I'm going back to the plane, and let's say what we will get. We will not get the Haldane model. It will have 4 states per lattice, so it's yet it has Chern number 1.
So by 4, what was your statement about 4?
So Haldane model it's on a square lattice with 2 states per side, and the model that I will cook geometrically will have 4 states per side. So 2005 is when Hickson and John Rowe wrote these 3 papers, one after the other, in Journal of K-theory, and 2005 was also the year when topological insulator came to stage. So it's a nice coincidence, and this paper are called Analytic Mapping Surgery to Analysis, and now it's this technique, it's called analytic surgery. And the classical surgery theory is a set of machinery aimed at deciding if a given simplicial complex or CW complex is homotopy equivalent to a manifold. So that was the original program, and these days you are in surgery theory, you will not recognize this original task or so now in this business, of course, topological obstructions are often useful in deciding that. I call topological obstructions, so they are not the complete topological invariance. It's just an invariant that you can calculate and decide more often that no, the 2 things are not equivalent. And among these topological, there was this signature invariant, which was people pay attention a lot, and these works were aimed at capturing the essence of this invariant, and they found that this invariant at least can be defined in context-free general C-star framework. I have two slides on that. So they introduced this concept of Hilbert Poincaré complexes. So you fix the C-star algebra C and an n-dimensional Hilbert Poincaré complex. So we have an index which goes from 0 to n. N will be the dimension of this complex, and then we have these spaces. They are not Hilbert spaces, they are Hilbert C-star modulus, so they are Hilbert spaces where the coefficients don't take value in complex numbers, but in this fixed C-star algebra. And then we have the map B, which should then gives us a complex, but additionally we have this linear operator T, which is or should be connected with the Poincaré duality, and it must obey these properties. So these properties were a little bit different from the classical, so we will see when we analyze our complete example, different from the classical setting.
So the big B is just the data of all the small b's, or
The second line.
Yeah, so yeah, the big B,
Integrated community.
yeah, so the big B is the small b. In our paper, the big B was the representation of small b. So that's the difference between the two. So also very important, T induces isomorphism of the dual complex. And then there is you can define morphisms. So there is a nice category of Hilbert Poincaré complexes, and also a natural notion of homotopy of these complex.
so you say this is different from classical, I don't know, maybe the RAM here you could do something like this.
Yes. So in the RAM you will get an operator P, and there is a little bit of massaging to get to a P, just the sign differences. So even ask Nigel how they got to this T.
This is the Hodge variable. No? Hodge stuff.
Yeah, it's related. It's related up to science. So we will see. So now, so we are not want to work with T, we want to work with this S. So when you, so out of individual spaces, you make the big space, and S is connected with T up to a phase. And then what they discover is that you take now, okay, I'm good with the big B, and you'll find that this self-adjoint operator B plus minus S are invertible. It's a little bit like the spectral localizer, I think. So they have of course, it's based a lot on these communication relations that you see here, but there is no estimate of the spectral gap. And numerically, I let the mathematical sample a lot of surfaces. The gap always comes to be of order 1. So I would like to have an explanation of that fact. So now that we have this invertible,
The S is self-adjoint as well, you say.
so S is self-adjoint seen from the big space pool.
That's why this I front there, so you need that. There's some computation to check that. It's not all.
Yeah, that's right. In fact, S, of course, will not leave these individual ones invariant. It will jump between different ends. But at the end, on the full Hilbert, on the full space, it's self-adjoint. So now, in the even case, if you have an even dimensional Hilbert Poincaré complex, and its signature is just a class of the projection into the positive spectrum of B classes, and the positive projection to B minus S. So this gives us the K-theory class in that sister algebra that we fixed. And in the odd case, you are looking at this unitary operator, and that defines a K1 element. And this signature invariant is invariant under homotopes of complexes. So that's important because it is this one which assures us that if you refine the triangulation, if you start with other triangulation, the value of this index will be the same. So it just this framework in fact solves a lot of questions. So here is my favorite example, which also tells us what's going on. So if I take n close-oriented surface equipped with the triangulation, then the simplices lift canonically to a universal cover of n tilde. And on this universal cover, the fundamental group X freely and properly, then a simplicial complex as lifted to the cover gives us a together with the standard Poincaré duality, furnishes us the complex that we look for. And what is the sister algebra here? The sister algebra is just the group sister algebra of the fundamental group. So out of any, what we get for free is that any triangulation furnishes a non-trivial K-theoretic class in that sister algebra. And for example, if you take M to be the torus, then phi 1 is E2. The universal cover is just the plane, and this one, the machinery gives us a K0 element, a non-trivial K0 element in C star of C, which is in the same class with the Halley model. Furthermore, they look.
Sorry, which type of models?
Which types of it?
You get C star models, C star models. What exactly are you doing?
Just the simplicial complex of the triangulation.
With values
In C. But these ones are immediately when we lift, yeah, because we had the. So furthermore,
so if you start with the rabbit, what do you get? I guess the rabbit is the sphere, or
yeah, yeah. So you get start with the rabbit, but you would like. So you get the signature. The signature is 2 in that case. The signature is 2 because we are taking the difference.
if you divide by 2, it's 1.
If you divide by 2, but the rabbit is has genus 1. So you have to do something else with the rabbit. You have to refine the
rabbit is genus 1.
No, it's genus 0. Genus 0. In fact, the rabbit was more complicated than as shown here, because while doing these calculations, I'll show you immediately, didn't come right. And then we discovered that this rabbit has 2 holes at the bottom, because that's how ceramic figurines are made. Hole in the bottom, and we discovered it with
You said that you put the triangulation in Mathematica, and
yeah,
computed and didn't get what you.
yeah, that's right. We discovered the holes. Analytic surgery. I will learn how to correct triangulation. So this one, the signature So if you consider a triangulation upon oriented surface, so upon infinite refinement of the triangulation, then the signature lands in the non-trivial K-theory class of the raw algebra of the plane. So Bani being a genus zero surface, I will have to look for full boundary correspondences and so on. I really have to refine the infinitely define the triangulation in the same time blowing up the figurine. And in that case, what you get? You get, if you're sitting at a point, refining the figurine, refining the triangulation, blowing up the figurine, you end up with a plane. And
But I will have a question.
Yeah.
If you haven't put any physics behind it, the only thing you can get is the Euler now. It's the only topological thing that you can get of the surfaces. You put a surface.
oh yeah, so
You should not get
now-
anything else unless you
that's right. So we'll put a lot of things. So here is a surface triangulation, and we are going to put resonators at the center of mass of the synthesis. And that operator B plus S will tell us how these resonators are connected to each other. And the connections are no more complicated than this. So imagine that these are cavities where air can vibrate, whistle, and then you drill a whole tunnel between these resonators, and this is how you will couple them. And I will tell you what these colors are. Okay, so now if you out of that triangulation you populate it with these resonators and you make these connections, and these connections come from the B operator and S operator, then you get the Chern number. So here is to stay anchored in the physics world. So here is a acoustic cavity. You'd like to have it elongated like that. And the first mode, so will be when the air undergoes a like this. So it will out of sync. So this is what this mode is. And if you increase the frequency, you will see more complicated modes, but they are very separated in frequency. So you can just work with this mode and forget about all the other ones. And then if you have two such cavities and you couple them with a tube on the top, you measure again what are the resonant frequencies. They are now shifted. And if you look at this shifting, it's very much accounted by such a tie binding or hopping term. If you do, so here is the point, is that we have a negative coupling, and the negative coupling will carry color green. And if you couple them like so, you get a positive coupling. And we will need a imaginary coupling, and the trick is to double the resonators. So now we are taking this as being one of these seen from above, and we have to do this connection, one positive, one negative. And if you do the energetics of this, you'll see that it's modeled by a complex coupling where I is in fact went into this matrix. So I has been ported in 0, 1, minus 1, 0 matrix. So now we are working with a model which have not one resonator per side, by two, and all the couplings are actually real couplings. They are as simple as putting tubes like this, and the whole dynamics remains the same. So it's a trick that we found to implement classification table of topological insulators with metamaterial, and you can, this type of trick reserves all the symmetries. So if you have those combinations of symmetries, you do this trick, then those symmetries are reserved. So it's the sure way to, and the easiest way, you don't need active matter or anything to implement models with complex coefficients.
So you say you can check that you can this way produce all symmetry classes?
Yeah.
All with the same, I mean, you must have some symmetry. I mean, there must be some sign of symmetry afterwards. How do you enforce, let's say, time reversal symmetry?
So the way it is, you take a model from the periodic table, the minimal model, and then this technique tells you how to implement this one as a tie-binding Hamiltonian. You implement it here. So take a C2 model. It has four sides. It becomes an 8 side, eight states per side. Okay, you implement it, and now it's time to check are the symmetries preserved or not, and like magic they stay.
This is all real value.
Now it's all real value. So I can
Product.
show you the realization of class D, which has the particle pole symmetry done with the this and tubes. It looks quite interesting. So now, so we put these resonators. I have resonators at the edges on the nodes, edges, and at the center of mass of triangles. And now each of these vertices will, each of these resonator, because it's tightly connected to a simplex, I can label them by the simplices themselves. This is the boundary map. We have the cup product between cycles and cocycles, and I have this P operator, which is the standard operator, where you take these cocycles and you pair it with the fundamental cocycle, which involves all the top simplices. But we are looking for a T. So here I was telling you that T is not enough. We are looking for this T, and here is the T which will do the job. And out of that T, I showed you how to calculate S. And now if we look what kind of connections we need are shown here. So these are those positive connections. These are those imaginary connections, and they are all first nearest neighbor connection in the same they do not overlap. So it's very important that you can do it by 3D printing. If they will cross, then you will be difficult to engineer such a material. But since they don't, then you can build it by a machine which builds materials layer by layer. So if we just look at the B, we forget about S, then the zero modes of this B coincide with the generators of the homology group. They should be 2 plus 2G. So here is these dots are where the resonator should be. The connections are done by Nigel's prescription, and you see we see for genus 1 4 modes, 6 modes. There is a little bit of a gap here. If I increase or if I refine the triangulation, then this gap will close. However, when I add the S operator, I see this gap of the order 1, and this gap is stable against refining the triangulation. As I said, it's just an empirical observation at this point. So now if I take the Stanford bunny, I put the model, we see again a gap of order 1. Now if I jam the resonators in this region, I see these edge modes, and the gap now is filled with spectrum. These are snapshots from a simulation where I place impulse right here, so I have a psi naught. Then I decompose this psi naught in the eigenvalues and eigenvectors of the Hamiltonian with these top resonators blocked, and I calculated the dynamics in this way. So now it's an exact calculation, and what we see is the signal going around as we expect.
But it disperses also, no? There must be some
So,
dispersion
well,
if you wait longer.
That's something amazing that there is. It can go, I think it will go 10 times before it dies. So this will be the simulation. And of course, there will be dispersion at the beginning, but some will survive on the edge. Let's see where it is. It's already went on the back and it comes here. And
So this is on the half bunny, yeah?
yeah, so
So
now
that's where the
everything
gap is,
else is blocked. And so the movie, it will go again, and I didn't see any difference in the mode, so it's really non-dispersive.
And it can't be, I mean,
It will,
let's say
but
if you make the triangulation rougher,
rougher.
then
In fact,
it will go,
yeah.
it'll be dispersed faster.
Yeah, so so here you see sometimes it blows up like that, and I was trying to figure out what's going on with this blow up. So every time when there is a tiny different coordination of the triangulation, then this.
But does this mathematically produce you rougher triangulations with less cells? Because maybe here you can't compute long enough to see something.
Yeah. So let me see. So if I'm going back here, so here this triangulation, although you will say that it's irregular, when you look at it like that, they look kind of nice, I have to say. So clearly Mathematica produces the nicest triangulations, same distances. Can be, so you don't see anything.
But you can make the radius bigger. So if you say,
So,
then
I have a way.
And then the question is whether it works as well or not.
To do so, this simulation here is done with fairly refined mesh. The movie, I think it's with a less refined triangulation. Let's see, I showed you in the beginning. I showed you the. Okay, so you are concerned about the dispersion of that. So here is the original 3D scan. It has 69,000 faces, and this one has 3094 faces. That's the one we use for simulation. And there is a way to start from this one and make it a little bit less dense. But it looks like a nice triangulation was produced anyway.
But you're going to have dispersion of the mode in any system, whether the edge data is
Totally flat, yeah.
Yeah. So there's nothing different about the body than there is.
But what happens here? So we have a good point that. So here we cannot draw the bands as function of k, because there is no periodicity k parallel. But if we could, then we will have H modes which goes kind of like that. In this curve, there should be a point where the curvature is 0. And that's the one which supports this dispersionless. So somewhere on this curve, the curvature now changes from, there is a point where curvature is 0, so the mode is dispersionless somewhere. Sometimes it happens to be right in the middle, but you are guaranteed that somewhere there is dispersionless. So that's why these edge modes are actually quite special. They don't disperse.
So at the beginning, you have some overlap of.
I have an
things all
overlap,
over,
whatever
they will
dissipates,
dissipate
and
you're left with it.
only this one stays power zone.
Why would the other ones?
Yeah, because the dispersion. So what happens if you generate originally a mode which you say it's fairly localized, we know it will move in time, but as it moves, it will slowly flattens. That's what typically happens, and this flattening is proportional with the curvature of the band. If the curvature is absent, we have no curvature, then this is dispersionless mode. It will stay like this.
So basically, is it a good image to say that all the ones with curvature, they sort of dissipate in the rest,
the one that I
and
see
this one
is
that's
exactly
the
that
one
one.
that you see turn around 10
Yeah,
times. Yeah,
that's right.
Sure, but there will be pieces. I mean, if you do it, for a sufficiently broad energy excitation, there will be pieces of it that overlap with the bulk bands, and those will disperse into the bulk.
Yeah,
But
yeah.
there will be pieces of it that just don't overlap with the flat region, but still live in the gap. And those should stick around. Unless there's something absorbing about your system.
So in the movie, you see the ones which overlap with the bulk are the ones that this is the D minus. So I don't have control because so these are the modes which overlap with the bulk. You see that they go in the bulk. Some already go around, but these ones will flatten, and then signal is lost here, but there's still a mode which will overlap with the dispersionless region of the mode, and that's the one which continue to go and go.
isn't it? I mean, at the end, shouldn't I just have like one or very few states?
Very few.
State being there, and I isolate them, and they are just like standing waves. You just have things spread out.
Yeah, at the end, everything should just dilute over the whole lattice.
But this is
Because Nigel was concerned of what's going on with this one. So in mathematics, I have to check that the wave function is conserved. So the norm of this, nothing was lost in the simulation. And they simply, there is amplitude slowly around all the points, but they are too small to be rendered in this image. And that's my explanation. This one is really the dispersionless part that remains.
But this should never be a standing wave eventually, right? Because to have a standing wave in
Yeah,
ideology,
yeah. There will not be
is kind of
there will not be a standing wave, but it
Yeah,
will
but
it will
minus
dilute.
Yeah, okay. Standing waves.
Dilute.
It's a traveling mode.
Okay, so that's what my last one.
Let's thank first.